hear me in the back. Um, yeah, thanks, Barry and Arthur and Peter for a great introduction on the Galaxy Halo connection and dark matter substructure. My name is Sebastian Monzon. I'm a rising fourth-year PhD student working with working with Frank at Yale. And yeah, today I'm going to be talking to you about constraining the low mass end of the stellar halo mass relation with satellite galaxies. So very briefly, we all know that the Galaxy Halo connection, the point is to link what we can observe, galaxies, to what actually governs the dynamics of the universe, which is the dark matter. And once we have this connection, we can study the physics of galaxy formation. We can infer cosmological parameters, like we'll talk about in a bit. And if we're clever, we can maybe probe the nature of dark matter. Now, oftentimes the Galaxy Halo connection gets boiled down to just these two very basic quantities, stellar mass and halo mass. We have this very beautiful picture of what type of galaxies and what type of halos over several orders of magnitude. And we're confident in this picture because of how many different groups and authors and different types of methodologies have come to kind of self-consistent stellar halo mass relation. But if you zoom in, and particularly below 10 to the 11 or so in halo mass, you start to notice that these relations diverge, and that's because a lot of them are extrapolations at this mass scale. And if you ask me, it looks a little bit like a frayed rope. That's simply because we don't have the same type of observations that we do at the higher mass end, these massive galaxy redshift surveys like SDSS that can help constrain awesome models like, for example, the universe machine. There's no real analogy to that at the low mass end, which is, of course, the same. But there are important steps being done, like we heard from Richie yesterday. Satellites around galactic analogs, SAGA, in particular, is impressive because they have 101 Milky Way analogs, with I think a total of around 400 satellites. They're a photometric plus spectroscopic survey, which gives them a lot of confidence in their membership probabilities. And the whole survey was designed to basically ask the question, is the Milky Way typical? But differently, how does the Milky Way compare to the rest of the universe? So yeah, we already saw this plot already from Richie, but just to kind of give you a scale, this is SDSS, 100 microparsec. This is the SAGA survey compared to 800 microparsec. But how does the SAGA survey help us with the stellar halo mass relation? They're of course not actually giving us any dynamical mass estimates for each satellite. What they give us is the number of satellites as a function of stellar mass, or the satellites as a mass function. And we have a pretty good understanding of what type of dark matter substructure, or what dark matter substructure looks like for Milky Way mass hosts. So you can use subhalo mass functions from, for example, an n-body simulation, or in our case, a semi-analytic model, to again connect the observable to what actually governs the dynamics of the universe. And the link here is pretty obvious. It's just subhalo mass. So in particular, what we use to get our subhalo mass function is what we call SatGen. It's work that Arthur developed as a graduate student at Yale, and the whole point is to populate merger trees using extended parsec theory. You then initialize the orbit of these subhalos using impulse statistics from a dark matter simulation. You evolve those orbits based on analytic potential, so you don't have to run into any of this numerical resolution artifact. And of course, the whole point of it being a semi-analytic model is that it's flexible with your choice of potential, halo response, even the cosmology. But most importantly, I think, is that it's incredibly fast. So a lot of these n-body simulations are just computationally expensive, and so getting several realizations of a merger tree is not incredibly feasible at this mass scale of subhalos. Okay, so in particular, what I care about is the halo-to-halo variance in subhalo mass functions. That's something that SAGA is kind of naturally observing in the satellite stellar mass functions. And what I care about most, I think, is the halo-to-halo variance that you get from the mass accretion histories. So what I'm showing here is this very silly plot of delta function. You'll see later why it makes sense, but this is a host halo mass distribution for a SAGA-like survey. So we could just assume that somehow SAGA only perfectly selects 10 to the 12 hosts. And if I run my SatGen code 10,000 times, for example, I can show some different mass accretion histories and how those different mass accretion histories impact, just based on out of the green line, the subhalo mass function. So the gray contours here show the halo-to-halo variance across the 10,000 realizations. Okay. Of course, Saga doesn't only select 10 to the 12 hosts. They have some limiting magnitude in host galaxy luminosity. And what is more likely is that they have some distribution of host halo mass. So what I've done here is just a 0.15 deck scatter in host halo mass distribution. And again, you can see the mass accretion histories, 10,000 realizations, and how that impacts your halo-to-halo variance and subhost. And again, just to be a little bit more extreme, what if we assume that they have 0.3 deck scatter? Okay, so these are the 3 samples of merger trees that I'm using. We have to talk a little bit about parameterizing the stellar halo mass relation. In the paper, we actually go and kind of explore all kinds of different physically interesting parameters that might go into what the stellar halo mass relation looks like at the low mass end. But just for the purpose of the talk, all I care about is the slope and the scatter, okay? Alpha and sigma. And what I'm showing here is stellar halo mass relation, this time not normalized by halo mass, and a single realization of a Saga-like survey from our catching. So what I've done is I've taken my subhalo mass functions, I've churned them through the stellar halo mass relation, and now I have a Saga-like survey. But how do we describe this Saga-like survey? Of course, in the real data, they have 101 NO2 analogs, all with different satellite stellar mass functions. One kind of, or before I go there, this is kind of 4 different hosts. This satellite stellar mass functions of 4 different hosts. You can see that they're somewhat consistent. But to combine them, you have to be a little clever. And I guess one basic thing you can do is just bin in stellar mass and create a cumulative satellite stellar mass function. But binning is less than ideal because often it means that your results depend a little bit on your binning scheme. And then you lose information about the host-to-host scatter. And you also lose information about the amount of mass mixing that goes into your underlying host halo mass distribution. So instead, what we're advocating for is the use of 2 different statistics, the distribution of 2 different statistics. The first is just the stellar mass of the most massive satellite per host. So that here is log m star max. And the second is the total number of satellites per host that you can observe, so above some given magnitude level. And we think that if you anchor these satellite stellar mass functions on the x-axis, which is of course the stellar mass of the most massive satellite, and the y-axis, which is of course the total number of satellites, you're not going to lose a whole lot of information because these satellite stellar mass functions are roughly consistent or roughly self-consistent. And most importantly, I think we're going to include the correlation between these 2 statistics, which I'm showing here with the Pearson rank of 0.53 for this specific example. The idea is that more massive hosts have more substructure, and that substructure tends to be more massive. So if you include more mass mixing, like we are doing in the S30 and S15 sample, you expect that the correlation should increase. Okay, so I've now outlined the basics of our forward model. First step is to create detached merger trees. Then we assume some stellar halo mass relation. We create a mock survey. We can then observe the mock survey in terms of these 2 statistics that I'm showing in panel D and E. And then we sample the posterior, the parameter space with an MCMC and compare our highest likelihood model to what we would assume for the stellar halo mass relation. So what we're doing is we're playing this parameter recovery game. These are the 2 main driving questions. What constraints on the stellar halo mass relation can we get from surveys like Saga? And how does host-to-host variance impact these constraints? So again, just playing these simple parameter recovery games, what I'm going to do here is I'm going to vary alpha while holding sigma fixed. So I have 4 different permutations of alpha, 1.5, 2.0, 2.5, and 3.0. Again, alpha is the slope. And then I have the inferred value of alpha versus the inferred value of sigma. And if you just pay attention to the top panel, you can see the violin plot shows our posterior distribution from the MCMC. We're doing pretty well at recovering what we've input into the model. And the same is kind of true with sigma if we assume kind of a reasonable value of 0.2 dex, which is roughly consistent with the higher mass end. And this is for the S0 sample. If we include more mass mixing in the host halo distribution, we see kind of the same thing, a little bit more uncertainty maybe, and similarly with S30. So this might, be a good thing. Oh, okay, well we can learn about the slope at least. But if we play the exact opposite of the game, and we instead hold alpha fixed while varying sigma, again here I'm showing 4 different permutations of the assumed value of sigma versus the inferred value of sigma, you can tell that we are completely off of the one-to-one line here. So I'll just kind of skip through S15 and S30 because they're more or less the same story. The idea here is that an assumed value of a deterministic relation, so 0 scatter in the stellar halo mass relation, is consistent with something that's kind of gargantuan of 0.4 dex scatter. Okay, so why can't we constrain sigma? Well, in short, the reason is that the scatter in the stellar halo mass relation needs to be huge before it impacts our statistic. So what I'm showing here is the variance in our first statistic, the total number of satellites that you observe per host, and the variance in our second statistic, the stellar mass of the most massive satellite, as a function of the scatter in the stellar halo mass relation. And the colored lines basically show the default value if you had no scatter. And you can see that you basically have to churn it up all the way to like roughly 1 dex before you start impacting the statistic. And that basically means that Saga-like surveys are dominated by halo-to-halo variance. Furthermore, and this is kind of a secondary effect, Garrison-Kimmel et al. In 2017 showed that the scatter in the stellar halo mass relation is actually degenerate with the slope, and that's because of this effect called Eddington bias, where basically as you go down the subhalo mass function, you have a higher chance, because there's more satellites there, you have a higher chance of upscattering a low mass system than you do downscattering a high mass system. And this is pretty well categorized, and again, this is something that we find in our analysis. Okay, so I'll just flash through these. Saga GR3 is an important first step in the right direction. They have 100 Milky Way-like hosts. We developed a forward model to simulate these satellite galaxy surveys. We think that the host-to-host scatter in a Saga-like survey is dominated by variance in mass accretion histories. Again, this S0 sample, the green line. And it'll be difficult to place meaningful constraints on the scatter in the stellar halo mass relation using current observations. Also, stay tuned for the paper because it was submitted a month ago or so, and hopefully it should be published soon. Thank you.
Thanks, Sebastian. Okay.
Hi, thank you for the nice talk. I'm Haley Bowden at University of Arizona. How many, do you have an idea of how many satellites, or like how many Milky Way-like hosts you would have to observe to be able to put constraints on that?
Yeah, that's a great question. Because we have this nifty little forward model, we can basically play these games, and this is the answer. So the survey depth is on the left-hand side, the survey size is on the right-hand side. So right now, I think nominally Saga's gold sample is 10 to the 7.5. Round contour, so not great. If you go down an order of magnitude in stellar mass, 10 to the 6.5, things get a little better. Going down to 10 to the 5.5, fainter system, not so great. But what really helps is increasing the number of hosts. So on the right-hand side, from 100 to 300, you're doing much better. And then if you somehow have 1,000 Saga-like hosts, you're killing it.
Yeah, thanks for the nice talk, and thanks, Haley, for asking the first of my questions. So, can you give any intuition for this number of a sigma about a dex? Why does it end up exactly there? Is it just kind of, is there any intuition to be had for that?
Yeah, so I think, so I guess the first thing I'd say is that at the higher mass end, here's not the same stellar halo mass relation, but similar indeed. This is luminosity. Higher mass end, we expect scatter to be roughly 0.15 dex, maybe 0.2 dex. What it is at the low mass end is kind of the whole point of the analysis, but I think Peter might have a decent guess that it should be slightly less than 0.6 dex. That's what I read in the Allen, I think, 2019 paper or something like that. But yeah, that's kind of the intuition we give. Yeah.
Okay, let's thank Sebastian one more time.